Lesson 71, net torque. We will be able to solve problems involving net torque. So first I've got to explain what net torque means, and then I'm going to show you two worked examples on how to deal with net torque. What we're going to do tomorrow's lesson is we're going to spend some time working on net torque in class, but I'm also going to give you guys some time. I'm going to try and give you guys some time today, but I think it's going to take a long time to go through the two examples I've got for you. And also, tomorrow I'm going to be giving you guys a little quiz on motion so far. So we've come up to the end of chapter 10, so we're about to move on to the ideas of energy. Even though I know it's technically not energy, I would still put momentum as part of energy, but whatever. So we're going to move on to energy. So I want to give you guys a quick test on what you guys remember from chapter 10 and chapter 9 before we move on. Just so I know what's stuck and what hasn't. It's not like a test. So when I say test, it's more of a quiz. It's not a test. It's not going to go in your reports. Don't panic. Yeah. So what did we do last time on torque? Last time we talked about what is torque. So this was our first lesson on torque. So our first lesson on torque was to start off with what is it? Torque is, for those of you that don't know, a force times a radius. It is a twisting force. If you think about compression force and tension force and normal force, torque is like a twisting force. Of course, it's not measured in newtons, it's measured in Newton meters, because you can get a different force depending on how far away you are pulling your twisting, and that's got to do with as well a lever kind of action. The longer the radius, the more torque you can get. Torque is linked to mechanical advantage in that way. It has to be at right angles. Torque has units of unit meters. When you measure torque, what we do is we say if it is going clockwise, we say it's positive, and it's going out of the page, going into the page, and when it's anti-clockwise, we say it's negative, and we say that it's going into the page, out of the page, sorry. But those don't matter too much. I'm just trying to let you guys know that for torque is a vector. Once we did that, we sort of talked about, well, why is it good? Torque is a really good way to describe how much force an engine can produce. It sort of gives a good way to know how much mass a vehicle can pull, and compared to like other measurements which might tell you how quickly a car or a truck can go from 0 to 100 kilometers an hour, this tells you, well, it gives you a good idea of how much force does it need to put into acceleration and stuff like that. It's usually used more, it is used with cars and stuff, but it's usually used more with engines where the work required is important. So if you're talking about a crane, or if you're talking about a lift, or if you're talking about some kind of car jack, that's going to be, torque is going to be something we're going to be interested in. And then what we did one example on this, where we looked at a bus driver applying a force. We said torque equals force times radius, 45 times 0.3. That's how we did that one, nice and easy. Then I set you guys some questions to do on 7.8, questions 1 to 4. There were only 4 questions anyway, and that was to get you guys some practice on it. Now, if you haven't done that already, don't worry too much. I will give you guys a chance on tomorrow, I think, to work through a couple of these questions. But let's talk now about net torque. Now, net torque is very much like net force. The net torque on an overall torque can be found by adding up all the smaller torques together. This is done by assuming that clockwise torques are positive and anti-clockwise torques are negative. A balanced object will have no net torque or net force. This is known as static equilibrium. I don't know how much about equilibriums you need to know, but I thought I would write that down anyway. So static equilibrium is where not just all the net forces are balanced, which is what you would see if you had a block of wood sitting on a table, but a net But this means that that also all the net torques are zero, and that's going to be important, especially if you think about a building. You don't want that building to have no net force but be twisting around. You want it to be pretty stable. So let's look at this seesaw on the left here. You got a father and his daughter would be my guess, or maybe his very, very small wife. I don't know. Or friend, whatever. And so the net torque in this case, the net torque is going to be zero. The reason I know it's zero is because they're not moving. There's no movement here. They're balanced. How do I calculate this net torque? Well, I know the net torque is going to be the sum of the torque from A plus the torque from B. Now that torque from A, because she's pushing down here, she's making her anti-clockwise. So we've got a negative force times radius, plus the B is pushing down on the right, so it's going to make it go clockwise. Plus, so I'm going to go force 1 times radius 1, plus force 2 times radius 2. And in this case, the net torque is 0 because they're not moving. And so you could actually use this to find out what these forces are, how far away from the pivot they are, just like how we did with all the other ones. The only difference between this and the ones that we've just been doing is that now we've got more than one of them. It's the same idea as the bus driver or the wrench turning the nut. It's just now we've got 2 nuts or something like that. So question here, someone, clockwise is positive, yeah. Clockwise is positive. So the reason why I said for torque A, it's negative is because she's pushing downwards. So that's going to turn the whole thing anti-clockwise. So if she pushes downwards, and that's going to make, oopsies, this torque here is going to make a anti-clockwise movement, whereas his torque is going to make a clockwise movement or positive. So that's how you would sort of figure it out. I'm going to keep this up for about another 30 seconds, and then I'm going to change the slide because we're going to go through 2 examples on this. And they're both interesting examples dealing with this idea of net torque and stuff, but we'll go through them slowly. Okay, so let's push on to do an example. Now this example is, yeah, I wouldn't copy down the diagram just yet, but trust me. I've got this quick picture here that I can show you. And there's a lot of text here, but I wanted to kind of give you this idea. The scale is set up with the pivot closer to one end than the other. And you can sort of see here that the pivot on the right-hand side is closer to the right-hand side than the left-hand side. One side has a downwards force. 5 newtons is 20 centimeters from pivot. The other is 50 centimeters from a pivot. So we've got some information we can add to our diagram here. We now know that one side is 20 centimeters away and one side is 50 centimeters away. How much force is required to keep this balanced? What mass would be needed to maintain that balance? So if I had a question like this, straight away I would be very annoyed by the question. So I'm looking at this question now, and there are so many numbers and texts and pictures and stuff. It makes it very difficult to do this question because there's so much going on. So what I'm going to do, and this is why I said don't copy the diagram straight away, is I'm going to attempt to simplify this picture. All I would do is, obviously I don't care about this. I don't care about these things. I think they're about a bit of a waste. All I really care about, and I don't care about these things either. All I really care about is this beam here, because that's where the torque is sort of acting. So let's redraw this. So this is what I would draw. It's the same picture, but instead of those massive gold brass looking hangers, I've just got arrows. Instead of those wires, I don't need them. All I need to know is where the pivot is and the distance away from the pivot. This also gives me some space to work through this question down the bottom here. So let's work through this. Because we know that we want to keep this balanced, that means we want to know two things. We want the net force to be 0, and we want the net torque to be 0. Now, for this case, we don't really care about the net force. We just know that whatever the force pushing downwards by these two objects is going to be balanced by an upwards force of the pivot. We don't really care about them too much. We only care about the net force. So that net force is going to be 0 because we want it to be balanced. So that means that we know that if we call this one here A, and we call this one here B, you might have multiple things. You may have multiple different weights sitting on here, which would have different forces and stuff like that. But what we can do is we can say our net torque is going to equal the torque of A plus the torque of B. This is the sum of all the torques. It just so happens that A is turning it in a clockwise direction, whereas B is turning it in an anti-clockwise direction. And you might be thinking, how did I know this? It's like, well, imagine if there was nothing on the other end of the piece of wood, then B would just spin it in an anti-clockwise. If there was absolutely nothing here, then it would spin around. This would fall down, so it's pointing downwards. So that means it's an anti-clockwise. Whereas if there's nothing on B, then A would spin down, so it was pointing downwards. So that means it's clockwise. So let's start to look at this then. That means that torque A is going to be made up of whatever this force is times 0.5, because torque equals force times the radius. So therefore our force is just going to be F of A times our radius, which is in this case going to be 0.5 meters, plus our torque of B, which is torque B is in the opposite direction. So instead of adding it, I'm going to subtract 5 newtons times, in this case, 0.2. And we know that this net torque is going to be 0. So then we can now go 0 equals 0.5 FA minus 0.5. 5 times 0.2 is going to be 1. Adding 1 to both sides. One equals 0.5 FA. That means that ultimately FA equals 2 newtons. And that's how I got 2 newtons down for FA. Now, if I just want to quickly add to that question, how much mass would be needed to required to maintain that balance? Well, we could actually just quickly work that out. Just by doing this, we go, well, F equals mg, we've got, or mass times gravity, we've got 2 equals m times 9.8, so therefore m equals, it should be about 200 grams. It won't be 200 grams exactly, but it should be about that. 2 divided by 9.8. It's going to give us 0.204. I'm pretty happy with that. So we would need about 204 grams, or a little bit more than 200 grams to balance this out. But yeah, that's how I would do it. So let's go break it down. What I did is I said, I'm going to calculate the net force to do the net torque. To do the net torque, I find out all of the torques acting on it. In this case, there are two. One turning it clockwise, one turning it anti-clockwise. So one that's positive, one that's negative. And then because they have to equal 0, I could use that to balance it out. Now you might have a situation where there are like 3 or 4 different torques acting on there, and then that would be the same process. You would just have to add different radiuses times different forces, or subtract different radiuses of different forces. Now, are there any questions about this? All right, if there's no questions, because I'm going to move on in about a second, so let me know if there's any questions or queries or issues. I am trying to put a lot of these lessons onto YouTube, but it takes me a long time. So definitely don't wait until I put them on YouTube for answer to copy these things down, because you could be waiting maybe a week or 2. Let's move on to the next question. The next question is similar, but it's a little bit more involved. So what we're going to do is we're going to look at this question. And this is, by the way, this question was, I wanted to do a question that was like the one in the book, but different. The one in the book instead had a seesaw, and that's fine. All I've done is, instead of using a seesaw, I've done a lever that's got a scale. It's actually exactly the same type of lever, in that you've got the pivot in the middle, but yeah, you've got, in this case, it's just about dealing with it. Oh, this is not the next example. This is just a quick little extra side point. I thought I'd better bring this up because we're about to refer to this in the next question. The center of mass on an object is like imagining a point where all the mass is concentrated. This is just as much, there is just as much mass to the left as the right. Now, we've done this already before, but I just thought it might be a good time to verbalize this now, because I'm about to sort of refer to something with it. When we refer to center of mass, we're just referring to the center of the object, like the center of mass for that object. Now, usually, pretty much always for physics for year 11 and 12, it's just going to be smack bang in the middle of the object. Honestly, when you start to get to year university level, you start to sort of think, well, maybe there's some other things to pay in mind. But yeah, it's usually in the center of an object. If the density of the object is the same in all dimensions, then the center of mass will be halfway point of all dimensions. So that's what this picture here at the top is. For a lump of wood, because the wood is the same in all dimensions, it's going to be in the middle. The mass of the hammer is a bit different. Obviously, there's metal at one end and wood at the other. So it's not, along this axis, along the hammer, is not constant density. So because it's not the same density, it changes density. Therefore, the center of mass is not going to be in the middle of the hammer. It's actually going to be closer to one end, because there's a lot more mass here. So, and you can figure out where the center of mass of an object is to see if you can balance it on your finger. You would not be able to balance a hammer on your finger if you put it in the middle, but if you move your finger all the way to the end, you could probably balance it. By the way, the center of mass doesn't need to be inside a body. It can be outside of a body. So for example, for a donut, the center of mass is actually here, because if you look, it's in the middle of all of these axes. The same could be said for as well for a curved surface. You know, if you've got a curve, then the mass would be in the middle here. But you know, it doesn't matter too much. I'm just trying to show you guys, hey, be aware that because I'm about to use this principle in about just a fraction of a second. So I'm going to quickly use that here. So I'm going to do this example before we run out of time. And I've got 8 minutes to do it, so we're going to power through it. And then if it goes too quickly for you guys, then I'm sorry, but you might have to take notes elsewhere. But yeah, a young boy builds a bridge over a river by laying down a piece of wood as a bridge. Okay, the piece of wood is 2.6 meters long and weighs 40 kilograms. All right, sure. The boy walks across the 1 meters, but starts to get nervous as he weighs 35 kilos and might break the bridge. What is the magnitude of reactionary force of the bank A and bank B? Okay, so this is an interesting question. So it's asking for a force, not a torque. Now, I could start to draw in these images. I could start to put in these lines here for how far away he's moved and how far it is and how much force is done by the boy and how much force is done by the bridge. In the previous example with the scale, we didn't care about the force of the wood in the scale because we were just looking at torques. But now, because we're dealing with force, we've got to worry about the force of the bridge because of gravity. And I could do this for this picture, which actually wouldn't be too bad. But what I'm going to do is I'm going to do the same thing that I did last time. I'm going to simplify this image as much as possible. And to do that, I'm going to get rid of the bank. Oh, there's also forces on the banks pushing up on the bridge. So those are all the forces acting on that bridge. And all the things that can create torque. But I'm going to simplify our object to look like this. So here's bank A, here's bank B, here's the force of the boy, here's the force of the bridge. And so we've got all this stuff going on. So how do we calculate a scenario like this? Let's put a couple more details in before we get onto it. So we know that the bridge is 40 kilograms, yeah? So that means that force equals mass times gravity, or mass times acceleration, which in this case is the force of gravity. 40 times 9.8, that's going to give us about 500 newtons worth of force. Nope, I got that wrong. 392 newtons worth of force, sorry. I'm doing that because having a mass is not very useful to us. Now the boy is 35 kilos. So let's do the same thing. F equals 35 times 9.8. Again, it's going to be about 350, but still. It's going to be a little bit less than that. 343. 343 newtons. Okay. Now, we've got one more factor we can put in here. We've got 1 meter being how far the boy walked across, and we've got 2.6 meters being how big the bridge is. But the one thing that we are missing is we're actually missing this distance right here. Let me just try and redraw that. We're missing this distance here. Can someone propose to me how far do they think it's between between this end of the bridge and this point here, which is the center of mass for the bridge? Who can propose how far away that is? Can someone write that down in chat? Oh, we've got an answer. Oh, I'm excited. 1.3 meters. You are correct, Kelvin. It is 1.3 meters because the center of mass is in the center of the object. In this case, 1.3 meters is right here. So now we have a way that we can calculate all of the torques in this bridge because we have all of the radiuses of all of the things going on. But before we deal with torque, I'm going to deal with force. Okay, because we know two things here, right? The first thing we know is that the net force, I'm going to do force in purple. We know the net force equals 0. Which means that if I add up all of these forces, then they should be 0. So if I go F net is going to be the force of A pushing that side of the bridge up minus 343 minus 392 plus the force of B. And we know the net force is 0 equals F of A plus F of B, and then 392 minus 243. $735. So what that means is we know that in order to keep this balance, in order to stop this from sinking into the earth that it's standing on, the force of A and the force of B have to balance out the downwards force. They have to balance it out with 735 newtons. You could say the normal force has to be 735 newtons, or else the wood would start sinking into the ground. So that gives us a good first number we can use. But that doesn't tell us what the reactionary force on each bank is. That just gives us a total force. So, but before I do this, I've just got one quick question. How much time have I got left? I've got no time left. Yeah, I've got no time left. I can't even finish this question. So what I'm going to do with this is I'm going to pause it here, but I'm going to ask one last question before I move on, before I leave you guys today. And that last question for everyone is this: which side of the bank do you guys think is going to need to push upwards with a greater force? Side A or side B? Which one's going to have a greater normal force, or do you think that they're the same? Which side, A or B, do you think is going to need more force? Write down your answer in chat. A is more force is what Kelvin suggests. What does everyone else think? Which one's going to need to push up more? Come on, guys. This is the last question, and then you guys can go. Brochung says B. A from Fook Lee. Let me get a couple more. A, yep. One more, and then okay, A. And that's the correct answer. A is going to have to push up more because there is more forces pushing down on the A side, so A is going to have a greater force. So even though it's 735 newtons is A and B, A is going to be more of that 735 than B. We're going to have to do some torque calculations to work out how much less B is compared to A. Now, if you said it was the same, then that would be great, because then all we need to do is divide this by 2. But I can tell you straight away that it's not the same. If you were to think about this, the best way to think about it is it not the same as this. If both of these banks were made out of paper, which one of them, or maybe even glass, which one would crack first? The answer would be this side. Intuitively, you think, yeah, we're putting more force on this beam, so it's going to break first. And that's exactly the case. So more force is being put on this compared to this. But we need to figure out how those balance. So I'm actually not going to solve that today because I'm looking at my watch and we're running out of time. And I'm not going to sit you guys any more work, but hopefully you guys have got a little bit of time now, as in when I say time now, I mean before tomorrow's lesson, to work on the finishing of 10.8, so the 12 questions. I will see you guys tomorrow. Thank you so much for listening. I will, if you guys got any questions, let me know. Yeah, cool.